Hello everyone. In this video, I will explain what is non-deterministic finite automata with null transition. That is a finite automata which is non-deterministic in nature and it can go from one state to another state without reading anything, without reading any symbol. It can take a null and it can move from one state to another state. NFA is a non-deterministic finite automata with null transition is a device more general than non-deterministic finite automata. We have already seen what are the relaxed rules for non-deterministic finite automata. All those relaxed rules, we have further added more relaxed device that has a capability of moving from one state to another state without reading any real symbol. It can move from one state to another state just by reading a null. Now, what is the definition? NFA is a 5-tuple Q sigma Q naught A and delta. Q is a finite set of states. Sigma is finite set of symbols. Q naught initial state that belongs to Q. A is the set of accepting state subset of Q. These 4 tuple remain same as NFA. Same as NFA. Also same as DFA. The only difference is in transition function delta. Here what we have Q cross sigma union null just with the symbol set of symbol perform union operation with the null. Null will be treated as one of the input symbol to the power set of Q. For example, if we have any Q with two states Q0 and Q1 and any sigma A or B, perform sigma union null. Now in this set we have null A and B. So and in the power set we will have phi Q0 Q1 Q0 Q1. So the delta is Q cross sigma union null to power set of Q. So for this example, Q, what will be the elements of Q cross sigma union null? We will have the elements Q0 with null, Q0 on A, Q0 with B. Similarly, Q1 with null, Q1 with A, Q1 with B. These are the elements of Q cross sigma union null and the function is from Q cross sigma union null to power set of Q. So we will have the elements here Q0 null, Q0 A, Q0 B, Q1 null, Q1 A, Q1 B to power set of Q will include phi Q0, Q1, Q0, Q1. The same non-deterministic feature here, Q0 on reading null, for example, can take a phi. It means there is no null transition for Q0. Similarly, Q0 on reading A is suppose going on Q0 only. Q0 on reading B is phi. It means there is no transition for B on Q0. Q1 on reading null. Suppose Q1 on reading null. Q1 is capable of taking a transition, Q1 null transition. It can go to Q0. Q1 on reading A, suppose Q1 on reading A is going on Q0 Q1, it means it is going to Q0 state as well as Q1 state. Similarly, Q1 on reading B, assume that it doesn't have any transition on it, it can take a pi. So the non-determinism remains same as non-deterministic finite automata, as well as it has one more new feature, that is a state is capable of reading a null and it can move from one state to another state. It will help in designing us the non-deterministic finite automata. While if we have this option of taking a null, reading a null and moving from one state to another state. Let me take any example. Suppose if we have this L language, any language 0, 1, 0 followed by 1 raised to the power n, 0 m, 0 raised to the power m followed by 1. I can just make this diagram very simply. 0 Q0 on reading 0 is going on some state Q1 where it reads any number of 1 as n is greater than or equal to 0, and make one more diagram. 0 any number of zeros is read and reading 1 it is moving to another state. Assume this state as Q2 and this state as Q3. What I will make, I will just join these two by a null transition. Q1 on reading null is going to Q2 and Q2 is having any number of zeros followed by a 1. Now in this diagram, second one, Q0 on reading 0, take it to some state Q1, and Q1 on reading 1 is going to some another state, say Q2, and take a null transition to Q0. This is 0, 1, 0, 1 followed by a null, again 0, 1 followed by a null. It is equivalent to 0, 1 raised to the power n for any n greater than equal to 0. Make this state as the final state. So this is again very simple to draw, and remember that for any string which is accepted for non-deterministic finite automata with null transition, the same string can be accepted by NFA as well as DFA. Now, how can I make this diagram? 0 any number of times. Take a null, move to the next state, make this also as the final state. 1 any number of times. Now this is non-deterministic finite automata with null transition. We need to make the diagram for this. When we have this is one of the application of non-deterministic finite automata with null transition. See this optional negative sign. When we have optional negative sign, what we can do, we can have null or start from Q0 on reading either null. When we have a positive integer, take a null, move, or negative sign when it is a negative number, move to the next state Q1. On Q1 read any number 0, 1 to 9, and from Q1 to Q2 0, 1 to 9 reach this state, let's say Q3, Q2, and make it as the final state. We can have any number following this number. So this is the example of signed integer. We can see the application where we might use this null when the sign is optional. Sign number When we have a positive number we will take null in that case, otherwise this negative sign will be taken, and we will have any number of values on Q1 from 0 to 9, and then again 0 to 9 followed by 0 to 9. Non-deterministic finite automata, NFA with null transition for this language is 0, any number of zeros, 1, any number of ones, just join them with a null transition. This is 0 followed by any number of zeros, and 1 followed by any number of ones. Just join these two diagrams with a null transition. So that makes the designing phase very simple. Now we have a concept of null closure. See the definition. If we have some machine with a tuple q sigma q naught a delta, and it is a non-deterministic finite automata with the null moves, and let there be a subset S of Q, the null closure of S is represented by null S, defined as follows. Every element of S is an element of null closure, as well as if there is some element Q that belongs to null closure of S, every element of delta Q null, that is delta transition function of Q taking reading a null, is an element of null closure of S. We'll take this as an example. Suppose if we have example Q naught on reading Q2, null is going on Q2, Q2 on reading null is going on Q3. Similarly, Q1 on reading null is going on Q4. Find out the null closure of Q1. Null closure of Q1, first of all, it has to be Q1. Q1 on reading null is going to Q2. Q1 on reading null is going to Q4. Q2 on reading null is going to Q3. Q3 doesn't have any null transition. Q4 doesn't have any null transition. So this is the null closure of Q1. Similarly, find out the null closure of Q5. Null closure of Q5, put Q5 here. Q5 on reading null is going on Q6. Q6 is not going to any state. It doesn't have any null transition. So we will stop here. Find null closure for the following example. This example. What is the null closure of Q naught? Q naught doesn't have any null transition. So null closure will be only Q naught. Null closure of Q1. It doesn't have any null transition. So it is Q1 only. Null closure of Q2 is Q2 only, no null transitions. Q3 on Q3 we have a null transition, it will be Q3, and Q3 on reading null is going on Q naught. Q naught doesn't have any null transition, we'll stop there. Thank you for watching. Thank you so much.